Welcome to day 54. We've really been working on some pretty tough problems here these last couple days. In today's video, I just want to talk about two of the problems from the homework from the book that I thought were fairly difficult that I wanted to take a look at. So the first one is the dinghy problem. It's problem 21 from the book. I forget which number. I think it was number 5 in your related rates 3 homework. So here's the problem. What we have is, there's the picture of it. So what we have is a boat, a dinghy, it's kind of a funny word, is being pulled in, right? So that rope connecting the dock to the dinghy is like a winch. It's being pulled in, right? So once again, hopefully we see the right triangle here is kind of sticking out to us. And we have two questions here. We want to know how fast is the boat approaching the dock when 10 feet of rope are out. We also want to know the rate of change of the angle theta at that time. So I'll put theta in my picture as well here. Okay. The first thing I strongly urge you to do is on your picture, only put numbers into your picture for things that are staying constant. So you notice the book added the number 6 in there. That distance is always going to be 6 because the boat is going to be staying in the water, right? So that distance there on that right triangle is always going to be 6, okay? But what about the other two sides of the right triangle? Well, the rope, I'll use capital R for the rope. If that rope is being hauled in, right, it's pulling the boat in, obviously that rope is going to be shrinking in length, right? So that's changing. So I'm not going to put, even though in the problem R is 10 at one point in time, I'm not going to put 10 in my picture. I'm going to put R in my picture. So I'm doing R for rope there. The other aspect, right, if that rope is getting shorter, it's going to be pulling the boat closer to the dock. So that base of that triangle there, I'll just call it B, is going to be changing as well. Again, I'm not going to put 10 in for R yet, and I'm not going to put in whatever the base is yet. I want my picture to have variables be letters, constants be numbers. Even though we're going to know those variables at certain aspects of time, I don't want to plug those in until after I do the derivative anyways. So I'm going to leave R there for rope, and I'm going to put B for base. So that bottom aspect of the triangle there, I just called B. You can use whatever letters you want, but sometimes it helps to choose letters that make sense to you. Okay, so here's what they say in the problem. Let me read it for you. It says, a dinghy is pulled toward a dock by a rope from the bow through a ring on the dock 6 feet above the bow, as shown in the figure. The rope is hauled in at a rate of 2 feet per second. Okay, so that rope, that's the important part here. That's going to go into our no column. We know the rate of change of the rope. Now, they said it's being hauled in at 2 feet per second. Is that, if the boat is being pulled towards the dock, is R getting bigger or smaller? Well, we have to know that R is getting smaller. So I'm not going to say dr dt equals 2. I'm going to say dr dt equals negative 2. Okay. And that's all that's in the prompt. Question A says, how fast is the boat approaching the dock when 10 feet of rope are out? Okay, so how fast is the boat approaching the dock? That is our need, right? This boat is traveling towards the dock. So to know how fast it's going, that's the rate of change of B. So we need dB dt. Okay? dB dt should also turn out to be negative in this problem because if we're getting closer to the dock, that B is going to be shrinking. Now, if that's for the speed, we'll just report the positive number, right? But we want to know how fast is that B side of the triangle getting smaller. But they also gave us some more information. Not only do we need to know how fast is the boat approaching the dock, but it's specifically when 10 feet of rope are out. So specifically at the time when R, capital R equals 10, okay? So now I need to know the equation that relates these three sides of a right triangle. Well, that's obviously the Pythagorean theorem. Again, this is just for part A here. The equation then would be 6 squared plus B squared equals capital R squared. Because 6 is a constant, we just leave it as 6. We never had to come up with a variable for that. We didn't have to call it height or anything because it wasn't changing. We'll just call it 6. It's always going to be 6. Okay, so now what I want to go ahead and do is do the derivative here. And now you might be saying, well, hold on. I know something else. That's great, right? I'm going to pretend like I'm not noticing what else I need here. And we'll kind of discover it organically. So when I do the derivative of 6 squared, that's just a constant, so it's 0. I'm not going to write 0 plus. I'm just going to know that it goes away. So my derivative here, I'm going to do the derivative of b squared. Well, that's simply 2b dv dt. It's good that dv dt came up because that's what I need. The derivative of r squared is 2r dr dt. Okay. I can get rid of the 2's because I got one on each side. And now I have to plug in. The problem is when I go to plug in, I can plug in r just fine. I can plug in dr dt just fine. It's okay that I don't know dv dt, but right now I don't know b. So I have two unknowns in here, right? But we can use this equation right here to solve for little b. And really, we shouldn't need that equation because at that instant, r is 10, right? So 10 squared is 100, 6 squared is 36, 100 minus 36 is 64. So b should be 8. But we should be able to see b is 8 without actually doing that problem, right? Because if this is 6 and this is 10, right? This is a 3, 4, 5 in disguise, right? They're all multiplied by 2. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. Okay, so I need to get that b equals 8 in order to solve the rest of this problem. Okay, so now that I know b is 8, I'm going to go ahead and solve this problem. So I got 8 db dt equals r is what, 10? dr dt is negative 2. So I get db dt to be negative 20 over 8, which reduces to what? Those multiplied by 4, negative 5 halves feet per second. I think that was the unit. Yep, feet per second. So I know that that aspect of the triangle here, b is shrinking by 5 halves feet per second. So if they want to know the speed of the boat, it's okay to report 5 halves feet per second, because that's how fast the boat will be going. Okay? Because that aspect of the triangle is reducing by 5 halves feet per second. Okay, good. B is about theta. They want to know the rate of change of theta. So I'm going to keep all my no's. By the way, I can now add to my no column that db dt is negative 5 halves. Okay? A lot of times they do this on the AP Calc test. Something you find in A is going to be used in B. We don't know if it's going to be used or not. I'll just write it over there so in case we do. Okay, so what we need now is the rate of change of the angle theta. So we need d theta dt. That's our new need. So what I need to do now is write an equation with theta. Now, this can be a little bit challenging for people to do, right? Well, it's trig, plus you have options, right? I know SOHCAHTOA with right triangles, right? So I could write a sine equation, I could write a cosine equation, or I could write a tangent equation. Now, I avoid tangent because its derivative is secant squared, and it's going to be kind of a little bit more of a nuisance to evaluate. Right? So I want to stick with either sine or cosine. And let's take a look at our picture to figure out which one would be better, sine or cosine. Now, up here we have theta, right? So sine is opposite over hypotenuse. The problem with that is both the opposite and the hypotenuse are variables. So if I use sine theta, I have to say sine theta equals b over r. So when I do the derivative, I'm going to have to do a quotient rule. That's okay, we can do the quotient rule, but it might be more advantageous for us to pick cosine theta as our equation, because cosine theta would be 6 over r. So I no longer have to do a quotient rule. So I'm going to choose cosine theta. I'm going to show you that the answer is the same whether you use cosine theta or sine theta. Okay? So here's I'm going to do it with cosine theta for my equation. So I know cosine theta has to be 6 over r. Now we still have that fraction that we don't super like. Okay? So I'm just going to rewrite this, right? We did derivatives towards the beginning of the year where I asked you to do the derivative of 5 over x. And what you needed to do is rewrite it as 5x to the negative 1. I'm going to do that same thing here. Before I do a derivative, I'm going to write this. This flips to this. Makes it way easier. Now it's an ax to the n form. I don't have to do a quotient rule. You can still do a quotient rule if you want. This just makes it a lot easier. So the derivative of cosine theta, we have to remember, is negative sine theta. And then I'm going to tack on d theta dt. The derivative of 6r to the negative 1 would be negative 6r to the negative 2 dr dt. In terms of evaluating, this will be easier if I write this as negative 6 over r squared dr dt. Okay? Now that I've done my derivative, I can plug in everything I know. Right now, I know what capital R is, and I know what dr dt is. What I don't know is what negative sine theta is at that instant. Well, opposite sine theta, sine is opposite over hypotenuse. Now that we've done the derivative, we can use the numbers, because it's at that instant. So we know b is 8 and r is 10. So we get negative 8 over 10, or negative 4/5 d theta dt equals negative 6 over r squared. R is 10. 10 squared is 100. And dr dt is negative 2, right? Yep. Okay. So I know that 2 can become a negative 2 can become a negative 1. This could become a 50. 50 and 6 are both divisible by 2. This can become a 3. This can become a 25. So I get negative 4/5 d theta dt equals, I have a negative times a negative here, so that's going to be a positive 3 over 25. Okay, the last thing I need to do is multiply both sides by the reciprocal of this, which would be negative 5/4. That 5 becomes, negative 5 becomes a negative 1, this becomes a 5. And I get d theta dt equals negative 3 over 20 radians per second. A challenging problem, no doubt, but doable. Let me show what it would look like if you would have chosen sine theta as your equation. If you chose sine theta, you'd have to do b over r. They would both have to remain constants. So now we'd have to do the quotient rule. Right? So I'll do the derivative now. I just want to show you what this would look like. The derivative of sine theta is cos theta, d theta dt. That equals the derivative of the top, which is db dt, times the bottom, minus the top times the derivative of the bottom, over the bottom function squared. Cosine theta now, right, when we use the constants, adjacent over hypotenuse, that would be 6/10, or 3/5, d theta dt, would equal db dt, I know from way up here is -5/2, times r, which is 10, minus b, which is 8, times dr dt, which is -2, all divided by r squared, which is 100. -5/2 times 10, that's going to be a 1, that's going to be a 5, so that's going to be -25 plus 16 over 100 equals 3/5 d theta dt. -25 plus 16 is what? -9. So we get -9 over 100 equals 3/5 d theta dt. And now I'm going to multiply by the reciprocal again, which is 5/3. 5/3. 5 becomes a 1, 100 becomes a 20. 3 becomes a 1, -9 becomes a -3. And look at what I get. -3 over 20 radians per second. Kind of cool when it works out like that. Okay, I wanted to do the hot air balloon problem as well. I don't think I'm going to be able to do that because the class is about to come in here. The thing to remember on that hot air balloon problem is they tell you that the hot air balloon is 65 feet off the ground, and it's going up at 1 foot per second. So we know dy dt in that problem is 1, but it said it was 65 feet off the ground when the bike was underneath the balloon, and the bike was going 17 feet per second. What you need to understand is the scenario of the problem is 3 seconds later. So after 3 seconds, how high is the balloon off the ground? Well, it went another foot in every one of those seconds. So it went up 3 feet farther. So you need to use y equals 68. We also need to know how far the bike has gone. The bike was underneath it 3 seconds later. Well, every second it's going 17. So you got to do 17 times 3, which is 51. That means that bike is 51 feet to the right. So x would equal 51. dx dt would be 17. Then you can solve that problem and it becomes a little bit easier. I wanted to show you that in the video, but we just didn't have time today. So hopefully with that explanation, it can kind of help you out a little bit. That's it for today. Monday in class, I want to just have some more time to finish up assignments 3 and 4 or any other ones that you're missing, right? So we'll have some time to work on those. I'll have some extra problems for you as well if you're done and things like that. But we're going to start working towards the assessment on this, which will be coming a week from today. Okay? It won't all be these crazy hard ones, right? We'll have a good mix of the straightforward ones and the more challenging ones. That's it for today, guys. I'll have a great weekend. I'll see you on Monday. 2 trains. Bye.